Thanks again for being here. So the title of my talk is Supercharging Analytics with GPUs. And it's a talk / demo. So I'll do some live benchmarking right after I show you the results. And so yeah, so what the benchmarking performance is basically between GPU, open source GPU technologies versus their CPU-based counterparts. So we've been using, on the database side, Postgres, which is my favorite database, on the CPU side, and Pandas, of course, widely used, most people use. So these are actually, very good products, and it's not a, this evening, this presentation is not a, bashing of these technologies by any way. It's just a showing, if you go over to the GPU-based technologies, what would they bring you to the table, and that's the important part. And so PDAL is for LiDAR data, so that is what I would benchmark and show to you. And on the GPU side, we have OmniSci Core DB, which is OmniSci used to be called MapD, which is now called OmniSci. And so that is one of the great right now open source GPU databases. And they have also an enterprise level on top, which you will get some familiarity over that too. And cuDF is the new GPU data frame from NVIDIA, and which is performing very well, and I'll show you some of the results on that front as well. So one quick but important note here is that this is an independent benchmarking project, which is basically to say that none of the vendors or the products or the product developers were involved in the development or getting these results. I just basically shared the result with some of these vendors after we were done with it. So there's no influence from the vendors here. We're happy to have OmniSci co-sponsoring the event of today, and they were obviously happy with the results that we got out of the benchmarking, but there's no influence in terms of what I'm showing you tonight based on who's sponsoring or who's present in here today. Just a quick overview of layout of the presentation today. I'm going to just very quickly on my bio. I'm going to jump into straight to the results. Third section, code walkthrough. So I'll show you some of the results that you will see in the slides. You'll see live as we get them, and of course the Q&A at the end. So quickly on myself, I'll give a shorter version this evening. Is that in the past few years I've been working in a variety of data science projects. So it's big data design and optimization specifically on Hadoop platform, on distributed applications, and two major deep learning projects. One was one on transport mode detection with LSTM models from telematics data, one from images and detecting cracked equipment out of images with convolutional based networks, and recently data mining application out of streaming data to detect patterns of alarms that are coming from network elements from some telecom carriers. So these projects basically, from most of them, I had to sort of hack into the platform and bring different components, geospatial, time series, in order to be able to get the project done. And so that got us the idea of building in a platform from scratch that already has these components, and that is what we now call Unaltica. Concerning this evening, we also integrated one of the things that were on my wish list, which is a GPU database. So OmniSci some time ago open sourced their product, so their core product is open source, and that's why we have it included here. And so OmniSci Core DB is an open source project, and they have additional components regarding visualization, those are also some of them open source, but they have an extensive part that are, if you want to do multi-node GPU databases, or if you want to connect the ODBC driver to do business intelligence, etc., those fall into the enterprise side, and so you can follow up with them to get those features if that is of interest. But for now, what's in our platform as well, Altica, is the basic core component, which is the GPU database. So actually jumping right into the results here, and I'll walk you through this slide slowly. On the top right, which is the data specs, so the data results are basically from, there are two data sets that we are benchmarking today. One is the financial time series data, which is basically about, probably just read it over here. So it's about 20 years of 63 ETF symbols. ETF, think of it as stock data, basically. If you're not familiar with ETF, exchange traded funds, which is basically stock data. So it's per minute data for this for all of those 63. But the minute data is there if there was a volume. There was a trade made. So if there is no trade, the record is missing. So it's a sparse data. All in all, we're looking at about 50 million records here, rows of data, which in terms of CSV files, it comes down to about 3.5 gigabytes. When we load it up into Pandas, it's going to take about 6 gigabytes in memory, in RAM, system RAM. And when you load it up into a GPU data frame, it's going to take up about 5 gigabytes in the GPU memory. So that is the memory footprint. The second data set is going to be the LiDAR data, and I'll explain that when we get to that part. So this is the first data set, the first benchmark, which is the financial time series. The hardware specs, just so that you know what we are running on today, is there's a CPU node worker, which is basically we're using two machines out of our platform. One is a CPU worker, one is a GPU worker. CPU, each of the workers has identical RAM, basically about 60 gigabytes RAM on the machine. They have identical CPUs, 4-core, 8-thread CPUs, and the GPU card is a V100, NVIDIA V100 on the GPU machine. So except the GPU card, basically the two machines are almost identical. On the results on the left, so you probably have noticed the GPU numbers are on darker blue, and lighter blue is the CPU numbers. They are divided into two sections on disk databases and in-memory data frames. So the point here is that we have divided into two categories, because we have basically selected the data set so that we are in the sweet spot that all of these four are in the running. So if the data set is too small, then the overhead of using a GPU database is not worth it. If you are too large, then it might not fit into either RAM or the GPU memory. So we are in a spot that all of these they can compete, and then we can validate the performance between them. So that is the point of us going with this specific data set. So on disk database, basically data is on disk. So the database engine needs to go and read it from disk. That's the overhead that both big databases have to incur. And there's an in-memory data frame. So those are data set that is first we load it into memory, and then we do the benchmarking, so that basically there's no I/O overhead imposed on the component. So that overhead is removed. Probably last note is that we are showing first run results for OmniSci, which by that what I mean is that if you run a specific query on OmniSci, it often caches some intermediate results, and the next time you run the same query, it's going to go much faster. So that is out of the box optimization that comes with OmniSci. And Postgres, I'm not sure how much of out-of-box caching it has, but I haven't seen it any caching kicking in at least in the queries that I'm going to show you this evening. So being an independent benchmarking means that we basically have gone with out-of-the-box configuration for all of these four, specific to databases. So there's no optimization done or of any sort. These are what the performance what you get is just like a throw out the data there, and then that's the performance you get. And if you do more optimization, for example, on Postgres in terms of index creation and whatnot, that's going to give you better performance, obviously. But those people have the luxury of doing those things when you're talking about some mature BI reporting that is constant, that's machine, that's known, or certain queries. But if you, from the perspective of a data scientist or data analyst, that you just want to grab a data set that you have seen for the first time, and you want to just do some exploratory analysis on it, then there's no time to create indexes or whatnot. You just want to do quickly some exploration at the beginning, and if it matures to if it gets to a mature state, and that is a data set that you want to query often and you want to do different things, you get to optimization bursts. But at the beginning, so consider these out-of-box performances. The first query is, so this data set has about 10 columns. One is volume of trade, so basically number of transactions that have been done in that specific minute. And the query is basically calculating the mean and variance of that volume. And imagine 50 million records, calculating mean and variance of that. So on Postgres, it goes about 3 seconds, 1.6 for OmniSci, just over half a second for Pandas, and very low for cuDF, about 8 milliseconds. For OmniSci, and you will see in that live benchmarking that this is the first run result. So if I run the query again, it's going to go almost to 1/10 of this. So it falls into probably around 100 milliseconds to 200 milliseconds, and you'll see that. And actually, that's what you will see, because we have run this query before, so it's already caching the results. And this is a second query sorting operation. So it's the same column. This is the volume. Now we just sort it. You just want to say, put the maximum on top and then just descending order. And that would take about 11 seconds on Postgres, over half a second for OmniSci, 15 seconds for Pandas, and cuDF around 370 milliseconds. Third and last query that I'll show is a mixed operation, which means that basically we are calculating the return and then we sort it. So to calculate return, we pick up two columns, which is the data set. So open price, closing price of that minute. So at the beginning of the minute, there's an open price. When the minute finishes, there's a closing price. So the return would be close, basically minus open divided by open, and then multiplied by 100. So that is a return in percentage terms, and then just sort it. So we calculate the return and then we sort it, and Postgres would need 13 seconds for that, 3.5 seconds for OmniSci, Pandas 10 seconds, and again cuDF around 300 milliseconds. So that is the three queries, and I'll actually walk you through how we obtained some of these numbers. So the code is actually on GitHub, and I'll have a last slide that you will see the URL, and you can grab everything that I'm showing tonight, this evening is already on GitHub. So the notebooks, the Jupyter notebooks are already there. All the numbers, results are already there. And this is the GitHub actually that you're looking at. And I have a version on the local copies of these files there, so I'll switch to that. But I just want to let you know that this has already been made public. So this is maybe what I want to explain just very quickly is that there's a data ingestion part, which is which I'm not going to run. Well, of course, I'm not going to run. All of the data is there. So this is ingesting basically to the basically reading the CSV files, those 633 symbols, into a Pandas DataFrame, and then also creating a Postgres table that contains all the data. So this is a notebook that basically reads up all the data. And I just want to give you some idea what that looks like. So just reading it here up to a single Pandas DataFrame. This is we are adding so this is the actual about 10 columns that I just told you about. So these are, for example, this is the open price, this is the close price, and this is the volume that I was just talking to you about. And we are just adding the operation here, that we are adding a symbol ID column here because we want to get rid of these strings. cuDF still does not handle strings, so we switch. We create a single ID per, which is an integer for each symbol, and then we're just going to drop this column so that we can proceed. That's the point of creating this. And importing the same data into a Postgres database. So later on, you can see that there's the schemas are there. The schema of the table, and you can see how that's what that looks like. And this is just queries to import the data to the database. And that's about it. So we have about 50 million records here, and that was what I wanted to show you. So I'm not going to run, so I'm going to just open up this one as well here. And this is all the same things, but now on the GPU side. So for reading up to the cuDF data frame, GPU data frame, and also ingesting data to the OmniSci database. So again, reading it. So we first create a Pandas data frame. This part actually you're gonna see in the other notebook, which is the performance benchmark. So I'll just save the explanation there. But the idea is that you first read the data into a Pandas data frame, and then there's a cuDF data frame that gets created out of the Pandas data frame. That's the operation that are here, and I'll explain that on the other side. This is just a GPU memory footprint that we have. Like for example, here we have this very Python notebook, which is taking about 4 or 5 gigabytes, and then there's a MapD OmniSci database that is running. So that is the footprint of the GPU memory, and this is now ingesting data to MapD or /OmniSci. And so again, MapD, when we want to ingest it, we use the same Pandas data frame, and there's a direct function to just create a database table out of it directly with one command, and that's the ingestion part. So just showing you some of the numbers that I just showed you, and I gotta go through this very fast because just so that I have enough time. So I'm gonna start the Pandas part, because this guy is gonna take about 2 minutes to read up from this to Pandas data frame. So I'm gonna let this run, and I'm gonna come back to Postgres. So this is the Postgres part. So it's basically connecting the database. So Postgres doesn't have at least in these queries, there's no automatic caching that is gonna kick in. So in these notebooks, there's a first run that is on top, and then there's a second run, which is a loop of 3 runs. So in the second run, as you see, the results are both about 3 seconds. So Postgres here there's no caching, there's no caching feature that is going to kick in. So the first number is going to be about 3 seconds, no matter you execute it once or more. So this is about 3.62, and this was the number that you had here. So it's roughly in the same range, about 3 seconds here. Sorting, this is gonna take a bit more, so 3 times 11 seconds. So this is gonna take a bit more time, but that 11 seconds basically, I save time. I show you already what's this, and this is the 11 seconds that we have here, and that's gonna give us what we're gonna see here. So if we run it once or more times, this is gonna give us almost the same results. So about 11.4. So it's this one's very stable. So this is the mixed analytics part for Postgres. So this is going to take 13 seconds 3 times. So I'll let this be, and I'll come back to our pandas part. So this read, and then I'll need to do some further manipulation here. So this is the creation of that symbol ID column, which is basically the ID column that is going to replace the symbol part, the symbol column, that because I'm going to drop this. So I'm using the same workflow basically on both sides. And this is the performance side. Oh, actually, on the Pandas side, there's no caching. This is in memory, so it's just we have only one version here. So I'll okay, it's not going to show me properly, so I'll just show you here. So this is calculating the mean and variance of that same column. So about just over half a second, and this was what you had here for pandas. So just over half a second here. For sorting is I think what we are expecting to see here is, okay, so this is going to take a bit of time. So 3 times, no, actually, yeah, 3 times 15 seconds. So this is going to take a bit of time. So I'll switch. I'll show you right afterwards. I'll jump back to what Postgres was running. So it's the mixed analytics, 13.2 on Postgres. So this was what we had here, 13.2. And we're done with the Postgres part. So this notebook, we can finish it, we can close it, and I'll just walk you over this. So this is the pandas, came back with 14.5, and that is, now forgetting what this was, it was the sorting operation. So the sorting operation for pandas was about 15, so we are in the range. And the mixed analytics is going to also be about 10 seconds for pandas. And that's going to come out basically the same thing. You can trust me on this. So I'm going to just close this one. So this is the parts on the GPU side. And we ran these on the CPU machine. So, and just to show you now the results on the GPU side, and which are basically running on the GPU worker. So the same story a bit about first loading up the data there. So this is for cuDF. And as I said, it needs to first read up the data into Pandas DataFrame. So you create a first Pandas DataFrame, and then we are going to create a GPU DataFrame out of it. Write lower in the notebook. So I'll come back to this. This is going to take about 2 minutes to read up. So I'll show you the results on the MapD side, which is the OmniSci Core DB. So the data is already, of course, in the database. So we are running it. We're connecting to MapD here. So this was the result 1.6 is basically what I had it in the graph. This is the first operation that I showed you. But when you run this a few times, basically more than once, you're going to get results which are in the lower bottom, which is now it's like 40 milliseconds, or stays stable around 40, 38. So the first one is going to be 1.6. And then because there are intermediate results cached, so it drops to about 40 milliseconds. So this is good. I mean, this is out of the box caching feature for this product. So that comes for free. And the same thing for the sorting operation. So what we had is the 600 milliseconds on the sorting for MapD, which is here. But then when you run it more than once, you're going to get the lower 24 milliseconds. So when you restart the server, that's one way to purge the cache. So you're going to see those higher numbers at the first run when you restart the server. But the later subsequent runs are going to drop much lower. And the last one is the mixed analytics for OmniSci, which is basically, so this is now about 30 milliseconds, 3 runs. But the first run was about 3.6, and that's what I had in here. So the numbers are there. So it's a matter of choice if you want to pick the first number or the later numbers. It's up to you. For me, I think personally, when I run something, it's the first time that counts most for me. But then if your workload actually is, you want to repeat it, or it has a repeated fashion, then maybe the second set of numbers are more appropriate to your situation. So it's up to you. But either way, you see that they are almost an order of magnitude, sometimes 2 orders of magnitude faster than the CPU counterpart. So they really do bring a lot to the table. So I think our cuDF is gonna be ready now. We read it into the table to a Pandas DataFrame. Now we just build a some steps to build that. So this is creating this ID column, and now building the cuDF from the Pandas DataFrame. So it's basically one function. cuDF DataFrame from Pandas. You give the Pandas DataFrame, and it's creating the GPU version. And the performance tests are basically as you saw. So 8 milliseconds here. Sorting. So there's some variance from run to run, about 374. So this is what we had here. It's in the middle, 374. And mixed analytics is 329, which is almost going to be close to what we had here. So that is how the numbers basically came out for our benchmarking. I think I'm done with this. So let's jump into the next data. Maybe just close this one first. So this is our second data set. It's a LiDAR data, aerial scan of Montreal. There are tiles that are split over Montreal. Basically, we are picking that tile there because my home is there. I wanted to see my home in the LiDAR data. And that's the La Fontaine Park up there in the tile. So the operation is basically, so that's actually another view. So that's actually not my home. It's a I'm not going to say where, but I'm the vicinity. So that's actually a senior resident high tower there. So this is Berry Street, Sherbrooke Street, just so that you get a sense of where this thing is. So that's the LiDAR data from this view, and the operation that we're going to perform is basically cutting that building out of this LiDAR data. So we're giving 4 GPS points that correspond to the 4 corners of this building, and the operation is just to cut that building out of this LiDAR data. It's a simple geospatial, very frequently done. So that's the basically benchmark, and that's the visualization of the building when it was cut out. And that is how it's the times that you're going to see. So just quickly on the data set on the top right, you see that it's for one tile, which was around that La Fontaine, and so the whole Montreal. I don't know, maybe 100 or 200 tiles. I'm forgetting the number, but one tile is about 18 million point clouds, 18 million basically records in the database, which on file compressed is about 80 megabytes of last file. If you decompress it to CSV, it would be with about 1.6 gigabytes. If you import it into OmniSci database, it's going to take about 600 megabytes in the database. And this operation is basically when you use PDAL, which is basically a state-of-the-art library, a point data abstraction library to work with point cloud data. And it's a very rich library. I use it a lot. And if you do this operation, it's going to take about 17 seconds to apply that filter of cutting that building out. And with OmniSci, it's about 268, and that is the first run, actually. On the second run, it's going to drop to a few milliseconds, maybe about 1/10 of it, 20 milliseconds. So it's very fast, and because I'm running out of time, I'm going to just show you the codes, but I'm not going to run them right now. But I can run them later in the evening if you want to see actually with your own eyes. I'm happy to run them for you. It's just that I want to leave some time for the rest of the program. So what I'm going to show you maybe is just the process of how you can verify. So on GitHub, we have this geospatial part. So the previous section was all this financial time series. The second part is the geospatial part. So you would see that there are markdown exports of those Jupyter notebooks. So same numbers, same thing, just in different format. This is the data ingestion part in MapD. So when we want to ingest data into MapD, so we get the file from City of Montreal. Thank you, City of Montreal. And then we need to manipulate a bit. There's a reprojection to bring this to the lat long spatial reference. And this is creation of table on MapD. So there's a geometry type that is automatically created from an XY that is the first and second column in data. So it goes really fast. It creates that data type automatically. So we have about 18 million records in the data set. This specific operation would take about 60 seconds. So this is how we push the data into OmniSci. And the performance tests are basically, I don't think I'm going to show it here. So this is the PDAL part. There's a pipeline that we gotta, so that's the polygon of the building. So around the building, we create a polygon, we define it, and we run this pipeline over the data. So that is the 17 seconds that you'd see. And there's some other information here that you can check on your own time if you wish. And I'll be happy actually to explain further later on. For the GPU part is basically same story. For OmniSci, we have the data is already imported into the database. So we connect the database, we do that cropping, and the cropping is, the first time is 260, and the subsequent runs comes down to 20 milliseconds. So OmniSci is a very good geospatial database. It has integration support for many operations. For example, this specific operation is something I do it frequently, so that's why I personally was interested to see, how fast I can do this, and so this how this whole thing came about, this whole project. So that is the numbers. I think I covered the main parts that I wanted to show to you this evening. Just final notes on the versions. I'll share this slide afterwards, but just so that you know what are the version numbers. So we're using CUDA 10, and the other versions are mentioned, so that you know what almost latest versions all front on these components. And the code and results are on GitHub. We love feedback, so send us an email on contact me directly, or on research@pattern.science. If you want to add something to this, if you're curious, operation Y or X, how fast that's going to go, I'll be happy. If it's not too much work, I'll be happy to do it. But if it's too much work, then we need to talk. We are on LinkedIn, so we've got future results or other events we want to co-sponsor, we want to co-organize. We're gonna put it out there. So one final note on that. I'm out of time actually, but let's maybe 2 minutes for questions. If you have questions, just one thing. Maybe you're gonna get a mic just so that the voice is captured properly.
Oh. Very basic question. Can you tell us more about OmniSci database? You say it's a relational database? Is it common data?
It's a relational database.
Okay, so it has all the normal relational. But it works on the GPU.
Yes. It's so if it can put it on the GPU memory, it will, but it has a graceful fallback on the CPU, it cannot. So basically the worst that you can get in terms of performance is regular CPU performance if it cannot fit everything that it needs to do on the GPU memory. But if on this, whatever I showed you this evening happens to be on the GPU. Well, it doesn't happen to be. We chose it to fit in the GPU memory.
Right. So for example, you have to change the columns. You couldn't, for example, say, oh, I have a mixed table, but put only those columns that are not fixed.
That actually, OmniSci has support for that. cuDF is still, yeah, it's the GPU data frame that still is numerical. But I've been following these guys on GitHub for some time. They are making fast releases, so I'm expecting, I'm sure it's on their roadmap to add that too. But with this version that you saw of cuDF, it doesn't take a strings column. So but the numbers are fine.
And the last question, I know there's a NumPy cuDF library. Did you play with that nowadays?
No, I haven't.
Okay.
Welcome. Any other questions? All right, we're good. Thank you very much, everyone.